Okay, I guess we can start. Good morning, everyone. The first two lectures this morning will be on flame instabilities, and then I will make some comment about turbulent flames, in particular premix turbulent flames. So I want to start with some, those projectors that is in my eyes need to be a bit lowered. Then I will try to increase your, you can come in. Is that good enough? No, it's too low. How about this? Same thing. Well, it's okay. There's a projector there that is in my eyes, and so anyway, so I want to start with some general comments about hydrodynamic stability. And so the first comments are here. Still, I'm not happy with the light, sorry. Goes all the way. Good. So some comments about general stability of fluid flows. And what I said here is many equilibrium states can be drastically changed by small disturbances. So the small disturbances start growing and growing, and then it moves the equilibrium to a different state. And so this is referred to as an instability. Of course, if the disturbance die out, the equilibrium state is stable. And those instability may sometimes be desirable. For example, it promotes mixing. Sometimes it's undesirable because you want to maintain the steady state. Otherwise, the instability could cause some damage to the combustor and so on. So the aim is to determine the condition when instability occur and when it's not. And that's the first objective. And the second objective is what is the new state that is developed thereafter. And so the decision-making of when the equilibrium is stable or not, it's usually carried out by what is known linear stability theory. In other words, you introduce small disturbances and you see what happens if they die out or if they keep on growing. And that sometimes gives you an idea of what may happen thereafter, but it's not really a description of the new state. To describe the new state, you need to do a nonlinear analysis, or often referred to as a bifurcation theory, as shown in this diagram. So, for example, if some norm of the solution is described here against some parameter, then let's say the equilibrium is given by the norm is equal to 0 or some constant. So it's described along this red line, and it becomes unstable at this point. So this is stable, this is unstable. So this is the point of the onset of the instability. And from there on, there will be a new solution that is established, and sometimes it's a bifurcation diagram, or this is where the solution bifurcate into the new state, okay? So the solid part of those diagrams are all stable solution. In other words, solution that you would observe experimentally. The unstable solution are not, because there are always disturbances in a system, and that can change the system from or move it from the equilibrium. In combustion, there are some intrinsic instabilities which are due to the combustion process itself, and those are the ones that we will be discussing today. And of course, there could be also instabilities due to the interaction of the combustion with the environment, such that acoustic instabilities, which is not going to be discussed in this talk. The theoretical consideration or investigation of instability is really straightforward. If you have an equilibrium, you just disturb it a little bit, and you see what happened with those disturbances. But practically, it's not a very simple calculation to do because that's not yet the one that I want to show, because the calculation is usually long. It lends itself to an eigenvalue problem. And the eigenvalues, which are the growth rate of the disturbance, I think it's something which will come in one of my next slides. The growth rate can be real or complex. So really, you have to search in the full complex field, and you have to vary all the parameters in the problem to see which one lead to instability. So really, numerically, it's a very elaborate thing to do, okay? Unless you look in a very narrow area to something very specific. Classical hydrodynamic problems of hydrodynamic stability problems usually start with a simple basic state, because if you know it's simple, you perturb it, at least the equation of the linear stability are relatively simple to do. Such an example is the Rayleigh-Benard problem, where you have a fluid at rest between two plates. The bottom one is heated and the top one is cold. So the basic state is just conduction state, as described in this graph. Temperature is higher and colder to the top and goes from the TH to TC. However, when you increase the temperature gradient, or you change the distance between the plate, or you change the properties of the fluid, it is known that an instability develops. And it develops when the Rayleigh number, which is described here, I don't want to describe the whole different parameters there. It's not really the problem of interest today. But anyway, if the Rayleigh number exceeds a critical value, then the conduction state becomes unstable, and there is a new state that develops, and that new state is the convection cells. Okay, you see it's more complex form of the problem. So you see there is an interest first to know when the instability occurs. Second, it's a mean to describe more complex fluid motion using stability theory. Just as a curiosity, I don't know if any of you know or have heard that, this is quite a famous problem in fluid mechanics. Rayleigh investigated by assuming, or maybe I should have said one thing about the Rayleigh number. For example, what happened is that the fluid is viscous. The motion is created due to the fact that there is buoyancy, and so the gases or hot fluid tend to rise. But if it's not, if the viscosity is not so high that it cannot just rise and remain stable, then the motion gets created. So it's a combination of those. So Rayleigh, in his investigation, actually included gravity as the parameter of interest. But it turned out after some years of investigation in this problem that the Benard observation of cells, convection cells, were not really due to gravity. They were due to surface tension effect, something known as Marangoni instability. But still, it kept that name for many years because of the pioneering work of Rayleigh and so on. So it's a curiosity that happens sometimes in science, and it's interesting. Well, anyway, in combustion, unfortunately, there are no simple solutions to disturb. There is no simple solution of a flame propagation or a diffusion flame or what have you, which is so simple that you can use the same idea or same vein as in this problem, which is a simple conduction state, no motion. So you have to start with a solution which is an approximate already. So it's one of the difficulties. So you have to start with a simple solution. So we're going to go historically to some of the simplest solutions that were studied or examined in the field. And the classical ones start with Darrieux and Landau, who investigated independently the stability of a planar flame. Darrieux wrote his paper and actually presented it, and that's again a historical note, published it or didn't publish it actually, presented it in the Congress of Applied Mechanics in about 38, but due to the war, it was not published. Landau, which is a well-known theoretical physicist, have published his paper in 1944. So the two exist. They were done independently, in fact, in slightly different ways also, but they attempted the same problem and get the same answer, of course. So some of us have the original paper of Darrieux, and it's interesting to read, although it's not in English, it's in French. So anyway, both have assumed that you have a planar flame that propagates at a constant speed. And so the mathematical description is very much in the same vein as we discussed earlier this week. It's the hydrodynamic model, in which the flame is an interface. On either side, you have the Euler equation with different densities, rho u in the unburned, rho b in the burn. You have to satisfy the Rankine-Hugoniot relation, which I wrote here in a simpler way or in a manipulated way. If you remember, I told you that we can rewrite them in this way using the fact that we know the velocity in the unburned gas, and essentially the jump in the velocity is proportional to the thermal expansion parameter sigma, or the density ratio rho u over rho b. There is no discontinuity, or the tangential velocity component is conserved, and there is a pressure drop across the flame, and the flame speed, which is the propagation relative to the flow, is a constant, is the laminar flame speed SL. So this is the mathematical problem. The first question is, does this model admit a simple solution or a simple steady state or equilibrium state? So the answer is yes, and here is the solution. And we have seen it already earlier this week. The velocity vary from, it's written here in a coordinate system which is attached to the flame. So there is an incoming flow towards the flame at a speed SL to retain, of course, the flame stationary. And then there is a jump in the velocity, a drop in the pressure. And even though I wrote here the solution with gravity, I am showing here the solution without gravity, and I will talk about gravity later. It's a mismatch. I should have left gravity to later, but the slide brought it earlier. Anyway, and the notation all along will be that the top in this curly bracket expression is always unburned, the bottom is burned. And remember the comment I made to you earlier this week, that when I wrote the jump in this way, rather than the Rankine-Hugoniot relation, which is equal to, or the natural form of the Rankine-Hugoniot relation, which is equal to 0, you have to know that the jump is always burned minus unburned. Otherwise, it's not clear, it's not consistent. Okay, so this is the planar flame solution, which is denoted here by U bar, P bar, and we introduce a disturbance denoted by prime. And the disturbance is much smaller or small compared to the basic state. And in stability theory, we rarely add a small parameter in front, but that's the idea. In fact, the small parameter enter in a certain way later. What is the small parameter? Is in fact the amplitude of this disturbance. So the idea is that the amplitude is small. Okay, but it of course enter in deriving the equation, because then the equation of motion, after neglecting the nonlinear terms, for example, there would be a term here, u prime v prime sub y, which is gone, and so on, okay? Reduced to this equation, you can manipulate the last two after integrating the top one with respect to x, the bottom one with respect to y. You use the continuity equation, you get a Laplace equation for the pressure, and then if you solve Laplace equation, you solve one of the two momentum. I wrote this one, you can use the other one. Once you know this one for u, you go here, you get v. So the solution in principle, it's not difficult to do. Furthermore, these are the jumps that end up after you linearize the equation. Now, as I said, and also the flame speed relation. So we have the equation, the jump relation across the flame, and the flame speed relation. If you just notice, it's a little detail, but if you notice, I wrote the jump across x equal to 0. And if you know, the perturbed flame is not x equal to 0, it's x equal to f prime. So what did I do here? Well, we use Taylor expansion to express the solution at a slight distance from the mean position into the mean position, because mathematically it's then easier to apply such a jump than to apply jumps at some curvy unknown interval. Okay, so these are the equations that need to be solved. The next step is always additional comment that pop up. I did it, but I didn't remember. So the point here is that we are interested to see how the solution behave when you wait long enough, namely what happens as t goes to infinity. Is the solution, are these perturbations die out and then u prime, v prime, p prime, and so on all goes to 0, or they grow in time, and that's the objective. So now it's a new slide. So we introduced normal mode. Remember, it was a linear problem. Linear problems are easy because, first of all, there is you can superimpose solution, okay? And the idea is you can use Fourier analysis. So basically, you introduce a disturbance of this form, which is one of the Fourier component. The notion is that the solution is a summation of all the possible modes as such. So the mode is e to the iky plus omega t. K here is a wave number, which is essentially the reciprocal of the wavelength. And A, which is introduced here, is the amplitude, which is in fact the small parameter in this study, or all the u prime, v prime, they are all proportional to A. Lambda, as I say, it's a wavelength, and I am going to follow the discussion in 2D, but there is no difficulty whatsoever to do it in 3D. All you have to do is introduce a wave vector, k1, k2, in the y and z direction, and the k that appears here is the modulus of the two, okay? So it's not true in general in every stability problem. Sometimes the three-dimensionality play a role because, you know, there's different physics there, but it's not the case here. So when you introduce this, all derivative by dy goes like ik times the function itself. and d by dt goes to omega coming from here. And so after substituting this, you end up with an ODE problem, okay? In other words, all the equations are ordinary differential equation. Again, the equation for P, U, V, now they're denoted by capital. Those depend on X only. Those are the jumps, and that's the flame speed. And note that this is a homogeneous problem. In other words, capital U, capital V, capital P equal to 0, A equal to 0 is no disturbance, right? And so the question is, are there non-trivial solutions to this problem? In other words, non-zero solution. And the answer is there would be, depending on omega. So omega is the eigenvalue in the problem. So it's a classical eigenvalue problem that needs to be addressed. And so the way you do it, you just solve the equation, you apply the boundary condition, and you obtain a relation or a solvability condition for omega, for the growth rate. So omega, in general, because we introduce the form of the perturbation in a complex form, right? I could have written this as ux e to the omega t sine ky plus cosine k, but introducing a complex form, then omega may be complex too. And so if omega is complex, it has a real part and an imaginary part. And so if you look at the flame perturbation, which is written as e to the iky, it's gonna, I collected here the imaginary part and the real part. So for the perturbation to die out, we need that omega r, the real part, is negative. If omega r is negative, as t goes to infinity, goes to 0, the disturbance die out. So what I am interested is to determine the eigenvalue, but in more specific terms, the real part has to be 0. If the real part has to be 0 for all perturbation. Remember, this was one of a sum of the infinite Fourier series. And so if it is for all k, then we claim that the basic state here, the planar flame, is stable. If it is positive for one value of k, then we say it's unstable because that disturbance may be the one that exists in reality. It can cause the solution to change dramatically. In the present problem, namely the planar flame, the parameters in the problem, there are only two. One was the density ratio, or the gas expansion, sigma, right? And the other one was the flame speed, the laminar flame speed, SL. So the functional dependence of omega will be something which depends on these parameters, on the wave number, and on the growth rate. There is no anything else. So that will be the solvability condition. And if I'm lucky and I can express this in an explicit form, it's going to be omega of sigma, SL, and K. Now, if you look at the units of each of these parameters, sigma has no units, it's density ratio, omega is 1/2, speed is centimeter per second, K is 1/2. So you can create the only creation of omega, appropriate unit, will be that it must be proportional to SLK, okay? Good, so we seem to know the answer, but of course we don't, because we don't know the coefficient in front, and this is the whole objective of this analysis, because that coefficient can be positive, negative, if it is real, otherwise the real part have to be examined. Okay. So we are in a way interested. I already denoted it by the growth rate of DL, Dario Lambda. So that's a notation that I will keep later today. Before we actually do the full problem, I want to do a slightly simple problem, and you'll understand in a minute why. So I'm going to assume first that sigma minus 1 is small, not 1, which is equal density, but small change in density. What it amounts to is essentially in those equations that were in the previous slide is that this term is going to be negligible. The reason is because if sigma minus 1 is, let's say, small like epsilon, u is of order epsilon v, you can verify those from, I mean, it's dictated really from the equation that they have to be of that order, and then this one will be epsilon squared, as you see. So it simplifies a little bit the equation. Not really to a great deal that if you don't, it's not going to be simple. But I said, hold, I will explain why. So you solve for P, you solve for U, you solve for V, you evaluate the jump relation, and you get a simple relation for the growth rate. Note that is, of course, proportional to KSL. And by the way, there may be slight different notation from what you have in the notes. I'm sorry about this. I tried to improve things in the last days. So, but what you have is correct, just maybe a different notation and so on. So omega has this form. So we see that the coefficient that we were missing is sigma minus 1 over 2 is positive. So the flame is always unstable, okay? The note that you will see here is one of the reasons why I did, this is just what I just said. This note is the reason why I'm doing this problem first. When sigma is much smaller than 1, you compute the vorticity on the unburned and burned side. Well, on the unburned side, of course, the vorticity is 0 because you have a uniform flow coming in. It's really irrotational, so no vorticity. But on the burned gas, we have learned this week that vorticity gets created at the flame. And so in principle, you can have vorticity. But when sigma minus 1 is small, it turned out that the vorticity is also small, so it's 0. So in fact, you have an irrotational flow in both sides, but there is something at the interface that is not obvious, and you will see it in a minute, and that's the reason that I did this example first. So if we look at the jump relations that we have used, one of them says that the change in the perturbation of u prime, note u is the not normal to the flame, but the vertical velocity. And v is the transverse velocity in the xy coordinate. So it says that it's the same, and in other words, and it's equal to f sub t. In other words, the propagation of the flame is equal to the vertical velocity at the flame. In other words, the velocity of the gas push the flame up or down, depending on the sign. The second one tells you that the tangential velocity has a jump which is proportional to the heat release, and it's proportional to f sub y. So let's look what happened here. Here is the mean position of the interface, x equal to 0. F is this function. So here the derivative with respect to y is positive. So the velocity on the burned side is smaller than on the unburned side. That's the blue sign, the blue vector. Here, f sub y is negative, so the sign is opposite, and so on, okay? It's just an observation directly from here. Now, what does that mean? It means that there is a vorticity created in this way, in this direction on this segment, and in this direction on this segment. So I show it here. So now when you have a surface that has vorticity, but there is no vorticity everywhere else, is known as a vortex sheet. So this is a vortex sheet, essentially. So what I said, the surface x equal to 0 across which the tangential velocity changes abruptly is a vortex sheet, which is a concentration of vorticity. And that vortex sheet impose or induce a velocity by so-called Biot-Savart law. So it imposes a velocity. So the motion that you see here and here, impose a velocity in this direction. Now that velocity, as we have seen here, pull the flame. The flame is pushed by that velocity. So it's pushed here, it's pushed back here, and so on, and that's the nature of the instability. Now, why did I do sigma minus 1 small? The reason is when I do now order 1 sigma minus 1, you see there is also vorticity in the burn gas. How does that affect the instability? I don't know. So it's a simple, nice explanation, but it's missing something. As it turned out, that vorticity is just convected further downstream, so it doesn't affect the flame perturbation, but I don't know that a priori. So that's why it's a bit missing, but it's a nice explanation, turned out to be also the correct one. So here now we consider sigma minus 1 order 1. We add that term that I killed before. It leads to all this new part of the solution in red. You compute the vorticity is not 0, but you can see that that vorticity, as you will see in a minute, doesn't really affect the answer. Now, when we apply the jump condition, we get I mean, those are algebraic relations because we know the solution. So when you put them in together, you're gonna get a condition for C1, C2, C3, the 3 constant here, and A, which is the amplitude. So you put it in a matrix equal to 0 for a non-zero solution to exist, which is what we are interested in. The determinant must be equal to 0, which leads to a dispersion relation, or a relation for omega. It's a quadratic equation. It has 2 solutions, but there is always one that has a which is positive. Since sigma equal to 1, it is positive, and this is the coefficient in front, which is the omega Darcy-Landau, the Darcy-Landau growth rate. So this is really what Darcy and Landau did. This is the conclusion that all planar flame are unstable, okay? It's known as the hydrodynamic or Darcy-Landau instability. And of course, the limit sigma minus 1 small is part of that, which is here. You see the growth rate increases, or the slope increases when increasing sigma. Sigma minus 1 is the weaker slope, and it further increases. Okay. This is the explanation I provided to you earlier, but there is another way to view it, and this is the following. If you examine the streamlines across the perturb interface, remember we did that a couple of days ago. We learned that the streamline across a slanted flame get always deflected as a result of gas expansion. It's deflected towards the normal. So the streamline here are deflected towards the normal, as you see. And the explanation based on this is simply that if you look at the stream tube far upstream, far downstream, if you go sufficiently far, it would have the same area. And due to, in an inviscid or incompressible flow, the area increase causes a velocity decrease. So there will be a decrease in velocity here compared to above, or compared to here. So the flame is propagating relative to a lower speed and therefore propagate faster. So it will propagate faster here. Here the velocity is larger because the different in area here compared to here, and so it will propagate faster. Now you can, of course, think that this is a perfect explanation, so why did I bother with the other one? But really that explanation is also a little missing because it assumes that the conditions are steady, but the flame is not steady, it's perturbed. So you cannot apply the idea of area velocity, which is a steady concept in an unsteady picture. So it's correct if it's quasi-steady. In other words, if the evolution is slow. So both explanations are a nice way to explain the instability. Okay, so now the Darry-Lerner instability, in fact, lead many ramifications of this instability in combustion, some of which I will show you. So if you start, for example, with a perturbed flame at t equal to 0, it's perturbed as such. It's a cosine with a small amplitude, and you let it propagate. It eventually, the convex, so I always confuse what I want to call convex and concave. So this is the convex towards the unburned gas. The unburned gas is here. They tend to expand or stretch, as you see. Okay? Oops, I did the same mistake I did a few times before, but we'll fix it. Not so easy. But the concave part, okay, bunch up and lead to a cusp at some point here, as you see in time. The motion can be described or can be constructed geometrically using Huygens principle. In other words, since the propagation speed at every point is a constant, you can make a little circle of radius SL, and you construct the next position. You do it at different points, and that's why you see that this segment extend like this while those punch up. Anyway, this is one observation. And indeed, sharp cusps are observed experimentally. This is a picture of an inverted flame. Remember, we talked about this week about the conical flame, but you can also get it inverted if you stabilize it at some point, say at the center or somewhere on the burner. So in principle, it's an inverted flame. The unburned gas is the dark, the burned gas, I'm sorry, the unburned gas is the bright, the burned gas, no, should say here. The bright, well, what it is, it's seeded with some drops that when they burn, they don't have the illumination anymore. And so that's why the burned part, which is here, I think the arrow is wrong, or it was supposed to show here. But anyway, the wording is correct. The burn is this region and the unburn is here. So you see that there are cusps pointing towards the burned gas, which is very similar to what I have shown you before. This picture was taken paper at Cornell with Gouldin and some other people here. Actually, the description of what I was just saying about the silicon oil droplet is written here. Also, you can see the formation of sharp folds and creases in turbulent flames. This is old papers found in Fox and Weinberg. You can find them in the book by Lewis and Van Elp, for example. There's a nice picture of that. Another pictures, which is rather taken by Uberoy, and I mentioned that name before because you wrote some interesting papers that were not very much paid attention over the years. Remember that the angle theta formed on a Bunsen flame is essentially, the sign of that is the ratio of the flame speed to the uniform flow coming in. And so clearly, when you reduce the velocity, you expect that the angle decrease, and I showed you some experimental photograph of that this week. So you expect that when it comes close to SL, you get a flat flame. But the flame is never flat. It always have that little kink on the sides. And that is presumably due to the hydrodynamic instability. Also, flames propagating in tubes are curved and not flat for basically the same reason. Okay, the next, so basically I wanted to show you that the fact that there is an instability, that when your perturbation grow in time, it leads to more cusp-like behavior is something that has been observed. But later on, we're going to see that we can also analytically plus numerically see that as well. Okay, so the next thing we want to talk about is downward versus upward. So I'm adding gravity, and here is the graph with gravity. There is no change in the velocity because velocity is obtained from the continuity equation. Gravity doesn't enter there. The only place where gravity enters in the momentum equation describes the pressure. And so what you have is essentially the hydrostatic pressure here and here, but of course with different densities, and the jump or the drop in pressure across the flame is described here. So this is again a solution of the model in the with the gravity. Okay, so we are going to proceed with the analysis, but before I do that, there's a comment here. It's just a mathematical observation, if you like, which simplifies the calculation. If I replace x with minus x, so basically instead of the flame propagating down, propagate up, or vice versa, it is the same as if I change g to be positive or negative, okay? So g, of course, the absolute value is the same, but it's like putting a minus. So I can do the analysis once, and if g is positive, it means propagating down. If g is negative, it's propagating up. It's just a simpler observation of, instead of doing the problem twice, if you like. And so if you do the stability analysis, very similar to before, the additional term is what you get here, sigma minus 1 g times k. Still a quadratic equation. It still have two roots, and there is always a positive root. You see that the additional term appeared here. So basically, even with gravity, planar flame are always unstable. That's the first conclusion. But of course, it's convenient, and not only convenient, but it's interesting physically to try to understand how does gravity affect the growth rate or the instability. What type of perturbation are affected or not affected by gravity? And so if you examine the long waves, you just examine this expression for k small. Remember k small, large wavelength, so long waves. You obtain that omega, the leading term goes like k to the 1/2, and then another term k here, and higher terms k squared, and so on, for small k. Now this term has a minus g, and so when g is positive, meaning propagating down, when g is positive, propagating down, then this is purely imaginary, right? And so the real part comes from the next term, and it's negative. So the real part is negative, meaning long waves get stabilized by gravity. But if g is negative, then this is a real quantity, and so the real part of omega is the first term, and so it's positive, and so it's unstable. So the long wave are stabilized by gravity when propagating down, but they get more unstable when propagating up. In fact, I don't want to get into that too much, but the first part is nothing more than the Rayleigh-Taylor instability, which is the instability between two different fluids of different densities. So that's what you get. So in a way, when you propagate up, because the burn gas, the hot gas is below the top, then then in addition to the Darry-Landau instability, you get also the Rayleigh-Taylor instability that make it more unstable. What happened for short waves? Well, short waves, you get exactly the Darry-Landau relation to leading order, so the influence of gravity is very weak for the short waves. Okay, that's the observation. Summary, the conclusion from the Darry-Landau analysis that planar flames are unstable. Nature does not permit flames to be too flat. That's basically the conclusion. The implication that if you carefully read the paper of Dario and of Landau, you will get the impression, even though he didn't say that explicitly, they say that planar or flame cannot be too flat, therefore they are probably all turbulent flames. But that implication turned out to be not correct, as we have learned over the years. So it sounds from their paper that that's what they meant. In fact, if you know about Landau, Landau was very much interested in the transition from laminar to turbulent flow, and in fact wrote simple expression that described this bifurcation diagram that I showed you before. How would the amplitude of a perturbation behave across or beyond the onset of instability to describe turbulent flow? So it's not surprising that that's what was in his mind, but it's a little interpretation of what you read in the paper. Anyway, there are a few questions that wonder in the analysis. The first thing is short waves are as we have seen, are also unstable. In fact, since the growth rate is linear, short waves, which are large k, seem to be even more unstable than long wave. And there is something missing there because the short waves, when they get to the order of the flame thickness, things within the flame can affect them. And that is not described in this model. And so that's one of the questions that we want to address. What are the influences of the thermodiffusive effect occurring inside the flame zone on the flame instability? Of course, the next question is, as I alluded to in the introductory comment of this lecture, that from linear theory, we only know the flame is stable or not. But what happens when they become unstable? That require a nonlinear analysis. Why a nonlinear analysis? Because we are assuming that the perturbations are small, and we neglect some nonlinear effect in the equation of motion. But this nonlinear effect can eventually cause some equilibration that, so if we wait long enough, the solution doesn't die out or explode to infinity, but get equilibrated, and we have to know how to obtain those from a nonlinear, or we learn what are these effects by a nonlinear analysis. And another question that I was in particularly interested is, how does Darry-Landau instability affect turbulent flames? Does it have any effect on them, or because the turbulence is there, then the instability is not important? So these are some of the questions that I want to address. So now we move to different, remember I started by saying in combustion, unfortunately, we don't have exact solution of simple basic state. So we base things on models. So the first model was a hydrodynamic theory based on the idea that the flame speed is constant. That's Darry and Landau. The next one is going to be a different model, which is based on the so-called constant density approximation. And I told you earlier this week the pros and cons of this approach. Of course, it's not highly physical in combustion, but the idea here is the following. Since when sigma goes to 1, you see that the growth rate becomes essentially zero, or it's neutral, not growing, not decaying, right? We can filter out those hydrodynamic disturbances and see what other effect could cause an instability or not. And so this is the so-called thermodiffusive model or the constant density model. Formally, the derivation of what I'm doing is essentially was obtained by Sierczynski, and the idea that heat release can be formally introduced into the equation was discussed in a paper by Matkarski and Sierczynski. Okay, so I already described this. Now the streamlines are parallel to the perturbed flame. They are not deflected. They're not affected by the flame. And so what is left is to discuss just the equation for the energy and the species equation, okay? This equation we wrote before. They are a little bit general. Of course, we're gonna look the assumption of constant conductivity, constant diffusivity. In fact, we will examine only a single reactant, which is a deficient one in the mixture, and so on. So this is, in principle, the problem that we want to address. Energy species of the deficient component. The structure of the solution is, in fact, as such. If you do it, let's say, if you solve it numerically, the temperature rise from the unburned to the adiabatic temperature, mass is consumed near in the reaction zone, which is thin, and omega is the reaction rate. And this is not an exact solution, so we're going to use the large activation energy approximation, which simplify the profile as such, with a condition at the reaction zone as we have described them by proper jump relation, or if you like, as a delta function for omega. Now, I did not use the word delta function this week. The reason is for a simple reason. Yeah, you can say omega is a delta function, but what is the strength of that delta function? Okay, so you have two choices, either to make it up, which is not something I like to do, or to derive it. And to derive it, that's the jump relation that we derived during the week that tells you what is the proper strength. Once you know what these jump, you can put it as a strength and analyze as you wish. But you know, the missing piece of information comes from the real analysis of the reaction zone. So I'm not going to show you much of the analysis because it is a bit elaborate, but the idea already I introduced it in the previous discussion of the Dario-Landau example. I brought this back just to tell you that there is only one single parameter in this problem, apart, of course, from the wavelengths and so on that we will introduce, wave number, wavelength. The only parameter that you have here is the Lewis number. And before I continue, I want to properly interpret the Lewis number. So we have a mixture with a deficient component. Lewis number is defined as the thermal diffusivity of the mixture, which is the abundant in the abundant species in the, it's based on the abundant species in the mixture, say nitrogen if it's in air, and mass diffusivity of the deficient reactant relative to that abundant, okay? We remember we used the idea of a dilute mixture where you have reactants with relatively small amount, so they diffuse into the abundance. The reason I'm saying that, because if you interpret the Lewis number differently, you can come up with all kind of conclusion, but this is consistent with the derivation. So in lean mixture, it will be the fuel. In rich mixture, it will be the oxidizer. Okay, the analysis requires to do it consistently, the mathematical equation, despite the fact that we have assumed a large activation energy, required to use a distinguished limit in which the Lewis number is not too far from 1. There is another theory that was derived in the 80s, which does not assume Lewis number close to 1. It turned out that based on that theory, all flames are unstable. So it wasn't a very useful one. And as you will see, in fact, the stability region is near 1. And so it turned out to be a good distinguished limit to examine. Moreover, there is nothing wrong in, so the little LE here is the deviation from 1, and it turned out that you can put even sufficiently large number, nothing change in the solution or in the equation. So as I said, there is no some singularity or something that happened when you use slightly larger than what you expect. When you say close to 1 doesn't have to be 0.1, it could be also 0.5, and if you stretch it to even 1 and nothing drastically happened, maybe it's still correct. Asymptotic theory never tells you what is the small parameter. It tells you only when the small parameter goes to 0, the approximate solution gets closer and closer to the exact solution. It doesn't tell you if it's good for this value or that value. That remains to the investigator, and I said that, and I repeat that because I think it's an important point. The judge and the jury is the comparison to observation, to numerical simulation, and so on. Theory is better if you can confirm it, or at least if it explains the right physics that you intend to describe. So because of that, it's sometimes called near equidiffusion flames, but as I said, it's not a big, really, limitation. So we are gonna introduce a perturbation as before. F is perturbed. Again, e to the iky plus omega t. Omega is the growth rate, k the wave number, t and y and all the other variables, that's etc. here are perturbed this way. And you will crank into the equation and you will get a dispersion relation, which is omega as a function of the reduced Lewis number and k, right? Like before. Well, it turned out that that relation is rather complex. It turned out to be cubic, like such, and these coefficients B naught, 1, 2, 3 are all given here in terms of those two parameters, LE and K. And omega in general is complex, so I have to treat it as such. So we know what these coefficients, so let's focus on this. I can write omega as omega real plus I omega imaginary and decompose this. So now from that relation I have two, one for that combine the real and imaginary part. I have to analyze it. So the marginal stability limit, which is when the growth rate or the real part is 0, right, leads to two relations here, okay? So in one of them, and omega I, which is the imaginary part, is still part of is still there. So there are two options here. Let's see if that's what I wrote. Yeah, there are two options. One of them is omega I is 0. It satisfies this equation identically, okay? And then from here you get that B3 must be equal to 0. B3 is a relation between K and the Lewis number, so that's the relation. If you look at it, it shows you that for this to exist, stability, there will be a stability boundary with some Lewis number negative. In other words, negative meaning less than 1, of course. I will draw that curve in a minute, but this is one stability boundary. Remember stability boundary because we have looked at where the marginal stability, where it separates between stable and unstable. Of course, we also have to examine those relations. Where is it positive, where is it negative? But it's an algebra thing. The next possibility will be that omega I is not 0. If an omega I is not 0, then from here you obtain its value, which is B3 over B1, or it can be checked that it's B2 over B0. Anyway, you get another boundary, okay? But you get another boundary and also the value of omega I. So the imaginary part on that curve is not 0, and we know that curve. And now I'm plotting those two curves. So the red one is the one that we found first, where the imaginary part is 0, and this is the second one, okay? Also the conditions show that it's unstable here and stable here, unstable here and stable here, okay? So in other words, the two boundaries don't conflict each other. If somehow your analysis show that it's stable here, unstable here, you must have done a mistake somewhere. It cannot be, unless there is another region, but there is no region in this discussion. I always point that to my student because sometimes you make mistakes. I mean, everyone does. And so always you have to check for consistency of things. So on the right, what you see is that when you cross that boundary, the solution on the right has grow. There is a range of waves that are unstable, that grow. And if you are here, then the growth rate, or the real part, because there is no imaginary, is negative, and so it's stable. On this side, you get curves like this, because they depend if you are between this point and that point, or between here. Anyway, it's a detail, I will skip that. Let's explain the nature of the instability, then we take a break. So the nature of the instability may be inferred, and I said maybe inferred because I said earlier you have to do a nonlinear to describe things, but nevertheless you can infer from the conditions that, from the marginal state. So if F is written as such, where omega I is the imaginary part, omega R is the real part, when omega R is equal to 0, the perturbation of the flame is described here in time, and this is for the marginal state. And you can have two possibilities. If omega I is 0, then there's a mistake here, I'm sorry. The T has only to multiply it's also a mistake here. The T multiply only omega I as it does omega R. So this T, so in other words, this bracket does not include both terms. It should be e to the IKY plus I omega I T. So when T equal to 0, when omega I equal to 0, this A is just A to the E to the IKY. Sorry, typos. But I catch them. So F e to the IKY, it's essentially it's a sinusoidal shape. And we interpret that, and it turned out to be a steady, because it doesn't change in time, cellular flame. In fact, if you go into the analysis, the detailed analysis, you see that the flame temperature behaves as such. And so it's easy to see that if you put a cosine, for example, that at the crest, the temperature is weaker than at the troughs, as you see here. And this is something which has been also observed experimentally. This is a cellular flame from a slot burner obtained, can be seen in the book by Mark Steen, who, of course, was one of the pioneers, as I mentioned earlier this week, of such analysis following Landau and Derry. The next thing is to explain the other limit. Well, in the other limit, when omega R equal to 0, then you can still have F e to the I omega I T. Now, this is also not correct. It should be e to the IKY plus omega IT. It's the same cut and paste. You see, that's the deficiency of nowadays computer. You cut and paste instead of rewriting. So anyway, it has an advantage, of course. But so you consider, so if omega I is not 0, it depends. If k is equal to 0, so in other words, there is no corrugation, then e to the I omega IT say that change in time, it pulsates. It's cosine omega IT, sine omega IT. So you have like a pulsating flame. And if k is not 0, then you get waves that propagate along that corrugated surface at a speed which can obtain from here or from above if correct. The typo is omega I over k. And that's what you can see here. You see at different times there is a sort of spread of the cells to the right, which probably has at that speed. Anyway, it makes sense. Okay, this is just a summary of what I said. So stable flame are obtained in some range near Lewis number near 1 based on that theory, and steady cells are observed to the left, traveling waves or pulsating flame to the right. One explanation for the cellular flame can be given. I know no explanation for pulsating flame. One can make up something, but it's not always convincing. The reason is it's very difficult to come up with an explanation of something change in time, because it must be related probably to different time scale and so on, and I haven't seen a simple, nice explanation for this. For steady behavior, in other words, when you move from one steady to another, explanation can be given because we can imagine sort of different states that can be caused by different physical mechanisms. So what you see here is maybe temperature isotherms or constant Y curves, which for a planar flame are just going to be parallel to each other and equidistant, if you like, if the temperature isotherm are small difference from each other. Now, once it becomes curved of cellular, then you see there is a bunch of, the curves bunch up in this region and spread out in this region. In other words, the gradients here are much stronger than here. And now it depends on the two gradients of temperature and mass and the supply of mass. Remember that the gradient of temperature or the temperature go to heat up the unburned gas, so the gradients are in this direction and the mass in this direction. Now, when the Lewis number is less than 1, thermal diffusivity is less than mass diffusivity. So you see I put the arrow smaller than here, okay? And so what you have is more mass coming towards the flame, and therefore it will propagate faster, as opposed to those sections where there is less consumption, and so it propagates slower. And that's, in a way, the reason why those tips keep on increasing. Those propagate less, but since it propagates faster, they create the cellular structure. And if you just write expression for, say, the Lewis number, remember thermal diffusivity divided by binary deficient reactant. So I will primarily focus on the denominator, thermal diffusivity in a propane air mixture. In fact, even hydrogen, it's not too different because it's based on air. But the molecular diffusivity or the binary diffusivity is different. So for propane, nitrogen is about that number. for lean mixture, and for rich mixture is going to be oxidizer nitrogen, which is there. And so you see that the ratio goes from, say, 1.81 in the lean case to 0.9 in the rich case. And so the tendency is that you're going to have a Lewis number less than the critical. Remember, -2, but -2 away from 1, namely less than 1, is going to be in the rich end. So rich propane air mixture are likely to have cellular flames, whereas in hydrogen air mixture is going to be the lean mixture that will have those cellular flames. Remember, those are not hydrodynamic instability, they are purely diffusive thermal instability. And that agree, generally speaking, with observations. These are pictures of a planar flame obtained in Marseille by Cuinar and Serby, or Cuinar without Serby, but it's the same lab. This is a cellular flame obtained after crossing the instability threshold. Note that the cells are approximately 1 centimeter or bigger than 1 centimeter wide, which is quite significantly larger than the flame thickness, okay? An assumption that we will use in the next lecture. This is a cellular pattern far beyond the instability, so after the bifurcation point significantly, so it's more pronounced perhaps. Those are pictures taken from Markstein. You see, I did not say that, but I should said that I should just briefly say that you know, I did say some of this during this week. Following the results of Dari and Landau, you know, I mean, Markstein was curious to see, well, how come all flames have to be unstable, whereas apparently people have observed them in laboratory under some conditions. And so he went to investigate that, and one of the introduction that he did, he changed the flame speed to depend on the local curvature of the flame instead of a constant flame speed. And I mentioned that this week. And there was, of course, a coefficient in front, which he did not have because it wasn't derived, it was assumed. It's an ingenious assumption, no doubt about this, but it's still missing something. So he went experimentally to get an idea that coefficient, when would it be positive or negative, and based on a variety of experiments, he had the right picture. Of course, that coefficient should be of the flame thickness order, and he discussed that. And we're going to see more about this in a minute. This is a last slide. Sorry, I know it's beyond, a little bit beyond, but I told you yesterday these lectures today are going to be stretched out a little bit. The pulsating instability, the little Lewis number, which is deviation from 1, turned out to be extremely large and seldom observed experimentally. I mean, people did observe, as you see, those experiments of cells flame, but I don't see them pulsating, with the exception of when they are very close to a burner. And the reason for that turned out to be, or at least it is understood, that the reason for that is due to the heat loss. So it turned out that heat loss bring the curves, the curve that is here, this is approximately 10 in the little LE. So if you multiply it by small beta, the reciprocal of beta, it turned out, you know, to be something above between 2, 3, something like that. And it turned out it's a large value, not common in combustible mixture. But when you have heat loss, it turned out that that boundary move to the left, squeezing the region of stability to a little narrower region, but bringing up to a value that is possible, in particular near extinction. So in fact, when people observe this on burner, they observe them usually in that range here, very close to extinction. So if they see those pulsating, but they change the concentration a little bit, then the flame go. And I know of some of these experiments, not too many, but yeah, they are observed, and it's quite nice to see. I think that's the end of this lecture. It says end, so it's the end. What we are going to talk about, please come back in between 5 to 10 minutes. What we're going to talk back about the combination or the combined hydrodynamic and thermodiffusive effect.